everybody. As we move through calculus, we have this intuitive idea of what a limit is. And today I wanted to look at the precise definition of a limit. So we're going to let our function be defined on some open interval that contains a, except possibly at a. So remember, as we're taking a look at a limit, we care what happens really close to a, but not actually at a. Our function, in fact, can be undefined at a, and we can still have a limit. So we say the limit of f of x as x approaches a is L. And remember, here is how we write that. And so L is going to be our limit value if for every positive epsilon, there is a positive delta such that the absolute value of x minus a being less than delta implies that the absolute value of f of x is less than L. So I want to take a look at this graph so that we can better describe what this limit means. So this first piece is saying that if the distance between x and a is less than delta, in other words, if we have an x value that's within delta of a, so either a minus delta to a plus delta, then this second piece is going to hold. Then that implies that our y value is within epsilon of L. So that's our limit minus epsilon to our limit plus epsilon. So again, what we're really saying is that if x is arbitrarily close to a, then our y value is going to be sufficiently close to L for us to say that the limit as x approaches a is that value of L. Okay, so here's going to be our process. Our goal is to prove that a value of delta exists for every epsilon. So to find that delta, what we're going to do is begin with the absolute value of f of x minus L being less than epsilon. We know our function and we know what we think our limit is. So that's where we're going to start. So after we substitute our known function and supposed limit, we're going to do some algebraic manipulations until we can end up with the absolute value of x minus a being less than some constant. And that ending constant is going to be our value of delta. So again, our goal here is to obtain the form of absolute value of x minus a being less than delta. So if we can find a value for delta, in this case, our value of delta is k times epsilon, then we have proven a delta exists for every epsilon, and that proves that the limit value is L. So we're going to take a look at an example here. So what we want to show is that the limit as x approaches 3 of this rational function is 7. Okay, so here our function is that rational function, 2x squared minus 5x minus 3 over x minus 3. Our value of a at which we're taking the limit is 3, and our supposed limit value is 7. So again, we're going to begin with the final statement, absolute value of f of x minus L less than epsilon, and work backwards. Again, we want to obtain absolute value of x minus a being less than delta. Since our a value is 3, we want to end up with something that says the absolute value of x minus 3 is less than delta. So plugging in our f of x and our L gives us this. So we're going to work some algebraic manipulations with this particular function. It's going to be easiest to factor that numerator. So the algebraic manipulations are going to differ depending on what type of function we have. Okay, so factoring that numerator, what you guys can see is that that allows us to cancel that common factor of x minus 3. And now simplifying one step further is going to leave us with the absolute value of 2x minus 6 being less than epsilon. Taking out a greatest common factor of 2 is getting us close to our goal. And using absolute value properties, we can rewrite this as the absolute value of 2 times the absolute value of x minus 3. Since the absolute value of 2 is 2, we can divide both sides by 2. And what you see is that we have achieved our goal of getting to the absolute value of x minus 3 being less than some constant. Here we have the absolute value of x minus 3 less than epsilon over 2. So again, since we were taking the limit as x approaches 3, and we now have the form of absolute value of x minus 3 being less than delta, what that means is that our delta is epsilon over 2. So epsilon over 2 or any smaller positive value is going to work here. And what we have proven is that there is a delta for every epsilon, and that proves that our limit is 7. I hope this helps.